Okay, welcome back for the third page of the first section of the 2019 Regents. The first question here is actually it's an interesting mix. It's a mix of some vector addition as well as some magnetism. So it says two identical stationary bar magnets are arranged as shown in the diagram below. You can see the two magnets. One is kind of horizontally inclined, the other one is vertically inclined. What is the direction of the magnetic field at point P? So two things that you need to know for this question. First thing you need to know is how a magnetic field looks around a bar magnet. Okay. It's very similar to the electric field questions that we did throughout the year. There's actually fewer field situations you need to know for magnets, and they are typically simpler. Okay? When you see a magnet, you're always going to see a north and south pole together. There's actually no such thing as just a north pole or just a south pole. They always come in pairs. So the magnetic field for a bar magnet typically looks something like this. The magnetic field lines start at the north pole, they curve around, and they end at the south pole. Something like this. And notice again, the field lines don't touch. And this extends throughout all of space. So if this was the only magnet in this question, you would see a magnetic field out at point P. Well, look where the arrows are on this side of the magnet, on the right side. They're all pointing towards the south end, the south pole. So you might expect that if this were the only magnet, you might see a magnetic field line that looks something, it's oriented like this. It's pointing towards the left, towards that south pole. But unfortunately, it's not. There is another magnet here. This magnet, this bar magnet, would have the same general pattern where the field lines from this magnet are pointing in towards the south. So let's imagine if this was the only magnet. You would see field lines at point P probably pointing in this direction, okay, towards the south pole. Now the question is, which way does the field line point when we have both magnets in place at once? Now it just becomes, we kind of isolated each individual case. Now this just becomes a simple matter of adding vectors, okay? We can add these vectors any way we want. We actually have them set up tail to tail right now. I could set up some tail to tail vector addition. Hopefully you remember that's where we already have the two vectors. We draw lines that intersect the head of one vector and are parallel to the next. Looking something like this. And really I should make these solid lines to show that they are vectors, not just components or something like that. So there's one parallel line for tail to tail. Here is the other. Okay, and the resultant points from where the vectors originate, where both of the tails are located, to where these dotted lines cross. So that would be right here. We can erase these other dotted lines, or you can leave them if you want. It doesn't really matter. And what we are left with is a resultant vector that points down and to the left, which is choice 3 on our page. So that answer is choice 3. We're going to move into a bunch of wave questions now. Looks like really the next, I think almost the rest of the page is really wave questions. That's good, because I don't think we've had any wave questions yet. And we are over halfway through this section, so that does kind of make sense. All right, a student claps his hands once to produce a sudden loud sound that travels through the air. This sound is classified as a what? This is just asking what type of a wave is a sound wave, okay? I'll only tell you the answer and I'll tell you the reasoning. The answer here is number 1. This is a longitudinal mechanical wave. Let's talk about the mechanical part first. Whenever we have a mechanical wave, mechanical means that with this wave there are actually real physical particles that are somehow oscillating, either back and forth or up and down. The way a sound wave works is when anything makes noise, say, clap the hands, what you're doing is you're displacing air particles. And then those air particles, because of the pressure differences, let's say you clap your hands together, what you're doing is you are making pressure differences in the air around your hands. Those pressure differences spread out. They essentially cause air molecules to be more densely packed in certain areas and less densely packed in other areas. And if you remember anything about pressure from maybe physical science, usually what happens is that particles that are under high pressure want to go towards low pressure. So those particles that are under high pressure will move towards the particles that are under the regions of low pressure. But what happens when all the particles that were in high pressure go over to low pressure? Well, now that region is high pressure, so they oscillate back. And you get this oscillation of particles moving back and forth. Okay? Because particles are actually moving, this is a mechanical wave. It is a longitudinal wave because the particles are oscillating in the same direction as the wave is propagating. Okay? As I'm speaking, the sound waves are moving outward from my mouth, and the air particles are vibrating parallel to the direction that the sound wave is traveling. So I'm speaking to the back of the room right now. The individual sound waves are vibrating, or not the sound waves, the air particles are vibrating back and forth, they're oscillating back and forth. That means that it is a longitudinal wave, okay? Transverse is something that oscillates perpendicular. I might have said perpendicular earlier. Longitudinal means parallel oscillation. Transverse means perpendicular oscillation. And what that would look like is your more typical picture of a wave, something like this. It's actually very hard to draw a longitudinal wave. An electromagnetic wave, we know that sound waves are not electromagnetic waves. They are not combinations of electric and magnetic fields. So, sound waves are longitudinal mechanical waves. Okay? 21. We actually had a note on 21 because 21 was a bad question. There were two possible answers for this. So we actually had to grade both of these answers as correct. The answer that they intended, I believe, was number 1, greater amplitude. Number 2 is also technically correct based on how they wrote the question. Let's actually look at it. Student generates water waves in a pool of water. In order to increase the energy carried by the waves, the student should generate waves with A. What they're trying to get you to remember here is that for every wave, with one exception, energy is proportional to amplitude, and it kind of makes sense. If you put more energy into splashing around, you are going to create bigger waves. If you're at the beach and you are standing in the waves, which type of wave is going to have more energy and possibly knock you over? The little tiny ripples, or the really big, like 6 or 8 foot wave that comes crashing down on you? Okay, it's the 6 or 8 foot wave that has a much, much higher amplitude. It's carrying more energy with it, enough energy to, cause you harm, put forces on you, knock you down, stuff like that. Okay, so energy is proportional to amplitude, the size of the wave, with one exception, except for light waves. That's the one exception. There were very famous experiments done that showed that that was not the case with light waves. The reason 2 could also be an answer the way this is written is because, and they should have just been more clear on the wording with this one. What a higher frequency would do would mean there are more waves happening per second. So really, if you think about it, what that means is that more energy is being transferred per second. If more waves are hitting you, more energy is being transferred past a certain point. Okay? And the reason that we can allow 2 is it says, in order to increase the energy carried by the waves. If we had just said, in order to increase the energy carried by a single wave, 1 would be the only answer. But because we pluralize wave for some reason, we have to allow credit for 1 or 2. Okay? Yep, that's all set. Let's go over to the other column. More waves. A wave generator produces straight parallel wave fronts in a shallow tank of uniform depth water. That is important. As the frequency of vibration increases, frequency of vibration of the generator increases, which characteristics of the wave will always decrease? So, we know how to measure a bunch of things about waves. We know how to measure the period, we know how to measure the velocity, frequency, wavelength, amplitude. Those are our big 5 things. 3 of those are linked together in an equation, okay, that kind of goes along with the first physics equation you learned, V equals d over t. And this is the standard equation for speed of waves. V equals f times lambda, f being frequency, lambda being wavelength, v being speed. Now, you do have to know some concepts about this, okay? We have found that if you have a wave that stays in the same material or the same medium, its speed will not change. The speed of a wave is solely dependent on the material, okay? All light waves travel the same speed in air. All light waves travel the same speed in water. All sound waves travel the same speed in air that is at the same temperature. So the material, which we call the medium, is what tells us how fast the wave is going to go. If the waves are in a shallow tank of uniform depth water, what that tells me is the material is the same. It's water and it's of the same depth. The depth of the water actually will change. For water waves, it will actually change how fast the waves move. That's why you see, I forget which way it is, if deep water means they move faster or shallow water, but that is, you can actually see that in action at the beach. Okay, so we know the speed is remaining the same. So that remains the same. I'm just going to put a little side arrow on top of that to show, okay, this is not changing. The frequency increases. In order for this equation to remain the same, if this stayed the same, then we wouldn't have two equal things anymore. This side increased, this side didn't. If the frequency is going to increase, we need the wavelength to decrease, because the speed is going to stay the same because the material, the medium, is the same. So that is choice 3. Number 23, a space probe produces a radio signal pulse. If the pulse reaches Earth 12.3 seconds after it is emitted by the probe, what is the distance from the probe to Earth? They're looking for a distance. They give us a time, and it seems like they don't say anything else, okay? It's very easy to skip over this. But it says that it produces a radio signal pulse, okay? A radio. Where have you heard the word radio before, other than in the thing that plays music and talk shows and stuff like that? Those forms of entertainment are brought to you with the help of radio waves. Radio waves are electromagnetic waves, okay? And electromagnetic waves in air always travel at the same speed, and that speed is c, the speed of light. Believe it or not, radio waves are a form of light, okay? Visible light is not the only type of light that there is. You can call radio waves light, you can call gamma rays light. Anything on an electromagnetic spectrum you could refer to as light rays. So that means that they travel at 3 times 10 to the 8th meters per second. That's their speed. Well, now we have a speed, we're looking for the distance, we know the time, this becomes very easy. So you have to remember, when you see that word radio, you're probably talking about electromagnetic radiation. 3 times 10 to the 8th meters per second. We're looking for the distance. The time is 12.3 seconds. When we do the math on this one, we should end up with a distance, I believe if I did my math right, of 3.69 times 10 to the 9th meters. Okay, that is how far away that space probe is from the surface of Earth, I suppose. Okay, 3.69 times 10 to the 9th meters. So that's choice 4. 24 should be very simple. Not really any math to go with this one, I don't think, if I remember correctly. Diagram below represents a light ray reflecting from a plane mirror. The angle of reflection for this light ray. Okay, so I see what they're doing. They're just giving you a whole bunch of angles and they're asking you, hey, which one of these is the angle of reflection? Let's label a couple of things first. The light ray that comes in towards where it meets the plane mirror, this is the incident ray. Okay? The light ray bounces off the mirror. Kind of obvious. This is the reflected ray. And we always measure any type of ray in a ray diagram like this from the ray to the normal line. The normal line is this dotted line right here. Okay? So from the ray to the dotted line, that's 70 degrees. And that should remind you that the incident ray is always, or the incident angle, the angle of incidence is always equal to the angle of reflection. Okay, or the angle that the reflected ray is at from the normal line. If this had not been a plane mirror, but some sort of maybe glass surface, and we have the ray going like this, that would be the refracted ray. That is light bending when it goes into a new material, but we don't have that here, okay? This is just a very simple question about trying to get you to remember how you should measure light rays, whether you should measure them from the surface or measure them from the normal line. Turns out you should measure them always from the normal line. So that is choice 2. 25 is kind of similar to 22. A light wave travels from one medium into a second medium. So one medium into a second medium with a greater absolute index of refraction. What that tells me right now is V changes. Going from one medium to the next. Index of refraction is the number that we have come up with that specifies, or that gives you an idea of how fast the object or the light is going to move. Which characteristic of the wave cannot change as a wave enters the second medium? Let me give you an example of this one with a light wave. One of the things I did earlier in the year is I took a laser and I filled this with water and I put like a little tiny bit of milk in there, so the laser shows up a lot better if you have some milk in there. And what we did is I shined the laser and you guys saw it bend through the glass and then come back out. Think about this. Did you see it change color? You shouldn't have. Okay? It was red when it went in. It was red in the water-milk combination. It was red when it came out. What does the color of a light wave represent, or which one of these variables is denoted by the color, or does the color depend on, I should say? It turns out that it's frequency. The color doesn't change. That is indicative that the frequency does not change either. Once a wave is created, you can't change the frequency of that wave. Okay, at least by the means that we're talking about this year. Okay, there are some very special cases in advanced physics where it can. That's not really what we're talking about. Once you create a wave, and it doesn't matter if it's a sound wave, a light wave, a water wave, or whatever. Once a wave has been created, its frequency will remain the same until that wave is absorbed, it dissipates, it gets reflected. Its frequency will stay the same. It won't change. The speed can change, the wavelength can change. Once the wave is created, the frequency does not. Last question for this little video. The speed of light, this little frequency right here, actually doesn't matter a heck of a lot. The speed of light in glycerol is what? So, we're looking for the speed of light. That's V. And there's a reason that it's not C. The reason it's not, that I'm not going to label this C, is because we're not talking about in a vacuum. We're talking about in glycerol. So what that tells me is we probably should look up something about glycerol. Okay? We need to look up its index of refraction. We need to know what the index is. So if we look on the reference table, and I've got my reference table hopefully right here. There we go. We look up on our reference table, we go to the index of refraction chart, we look for glycerol, we see that the index is 1.47. Okay? And we know that the index of refraction is related to the speed. If we hop over to page 5, we have this equation, the definition of the index of refraction. N equals C over V. What we're solving for here is V, the speed in the glycerol. We know N from the table. We know C because C is the speed of light in a vacuum. So I could write 1.47 equals 3 times 10 to the 8th meters per second over V. I solve for V by multiplying it to this side and then dividing both sides by 1.47. I end up with a speed of 2.04. I know you can probably barely see this, times 10 to the 8th meters per second. That is choice number 2. Okay? Please be careful on the math with that one. You could have eliminated these two options right off the bat because this is the speed of light in air. Glycerol is not air, it's more dense than air. Light should slow down a little bit. This is faster than the speed of light in vacuum. Nothing can ever travel this fast. It's impossible. And then you would have to determine which one of these the correct answer would be. So just a little more background on this equation right here, N equals C over V. You can think of this is the definition of the index of refraction. The index of refraction is given by the ratio between the normal speed of light in a vacuum and how fast light moves when it's going through a particular material. The slower light moves, the bigger N is going to be. So that can help you out if you're using that equation. That's what it's meant to do. I'll stop here and we'll get ready for our last Part A video.